2007 E&M number 1. We have an RC circuit here with a switch. They give us R, they give us C. They don't give us the battery, but they do give us a graph of the current through the circuit as a function of time. Note that this is in milliamps, and we start out with a y-intercept here of approximately 2.25 milliamps. All right, so for part A, using the data, okay, so this would be the data, calculate the battery voltage. All right, at time t equal to 0, the capacitor is uncharged, and that means all of the voltage drop is across the resistor. So we could say Kirchhoff's loop rule, starting on the negative side of the battery and then working our way around the circuit until we get to back around to where we started. We have voltage of the battery takes us up, voltage across the resistor brings us down, and then the capacitor brings us down the rest of the way, and we end up back on the ground. Now time t equal to 0, Q on the capacitor is equal to 0, therefore voltage of the capacitor is also equal to 0, and that's not needed. The voltage of the battery is E, and that's going to be equal to the current times the resistance of the resistor, which is this guy. The current that we're going to read off of the graph is, I'm going to guess, 2.25. If you want to guess 2.20, that might also be fine. So we're going to do 2.25, and it's in milliamps, so times 10 to the negative 3. And the resistance they give us is 550. So the battery that we're going to get out of the data is 1.24. And don't forget volts, because this is a numerical answer. All right, part B. The voltage across the capacitor at time t equal to 4. Okay, so we come over here to t equal to 4 and we take a look at the current. And I'm going to guess that that current is 0.35 milliamps. Again, this is going to be something that you have to read with your eyeballs, so you might get something a little bit different than the 0.35 milliamps. And we're going to use the same equation that I used up at the top there. We're going to have voltage of the battery minus voltage of the resistor minus voltage of the capacitor equals 0. And again, we're going to substitute in 0.35 milliamps for this, but this time now we're not going to have 0 for the voltage of the capacitor. So we're going to have 1.24 volts for the battery. We're going to have 0.35 times 10 to the minus third amps times 550 amps, and that's going to be equal to the voltage across the capacitor. Taking out my calculator and typing those guys in, I got 1.05 volts. I think that's the most straightforward way to do that. There is another way using the exponential decay curve, but we don't need to do that. Part C. The charge on the capacitor. Okay, well, if we know what the voltage across the capacitor is, then we can figure out the charge on the capacitor. So 1.05 volts times 4,000 micro times 10 to the minus 6th gets us 4.2 times 10 to the minus 3rd. And that's coulombs. You could also have 4.2 millicoulombs. All right, I'm going to have to clear out some things here and scroll down to parts D, E, and F. All right, for part D, sketch a graph of the charge. Well, as long as the capacitor is charging up from uncharged. Now, they told us that it was uncharged, so we're going to start at 0. And we're going to charge up here to an asymptote. And they sketch, and they don't say anything about labeling the asymptotes or points of interest, so I don't think we need to worry about that. But we do need to make sure that we approach an asymptote, and we clearly indicate that we have an asymptote to approach. All right. The power being dissipated as heat at 4 seconds. Well, for part E here, power dissipated in a resistor is going to be I squared R. Now again, I'm going to use that 0.35 milliamps, and whatever you picked for part B, that's what you're going to use here. So 0.35 times 10 to the minus third. Don't forget to square it. And they told us that the resistor was 550 ohms. So I get 6.7 times 10 to the minus, looks like fifth. And that will be in watts, the unit of power. All right, part F. Oh, we have check boxes here. Now we're going to discharge it, and we're going to replace it with a different dielectric, which means that now we can store more charge. The amount of charge on one plate of the capacitor is greater than. Okay, so we're going to say greater than. And we can use our rules for capacitors. So for a parallel plate capacitor, let's come back over here. If I run out of space, I'll go over there. So let's see here. We are going to, there. C nu equals, let's see, they said kappa is 3, so it's going to be 3 times C of the original. Now, our equation that we derived in class for charge on the capacitor is as follows. It's 1 minus the exponential decay, which is how we get this curve. And we need to take a look at how this C changes. So this is old. And then we're going to have Q new, which is going to be 3 EC, 1 minus e to the minus t over 3 RC. And when we plug in our values here, we're going to end up with Q new is going to be 1.63 Q old. Once we plug in a 4 here and a 4 here, plus we're also multiplying by 3 on this guy. That's where that, we don't have a 3 here, we have a 1.63 because we also have to change that exponential part with that 3 here. So the charge at 4 seconds, when we plug in the 4 there, is going to get us not quite twice the old one. So we're going to want greater than.